Hi, everybody. This is Saad. Today I have, I think, for the first time on this show, a neurosurgeon, Kevin Tracey. How are you doing, sir?
Very well. Thanks for having me on.
It's a pleasure. Okay, so let me just mention a few things about you. You are a neurosurgeon and inventor. By the way, my 13-year-old son today, who knows if he'll change his mind, today he says that he wants to be a neurosurgeon. So maybe you are the hero that he needs to speak to. So, neurosurgeon and inventor, president and CEO of the Feinstein Institute for Medical Research. You're a professor of neurosurgery and molecular medicine at Hofstra University. I could not believe your Google Scholar metrics. What's going on, man? I got to get my act together. 138,000 plus citations, which for those of you who don't know, that's a pretty big number. Your latest book, The Great Nerve, The New Science of the Vagus Nerve and How to Harness Its Healing Reflexes. So let's start there. What is the vagus nerve? Tell us all about it. Keep it at a layman's term. My audience is very smart, but don't bore us with the specific neurotransmitters and so on. Take it away.
The vagus nerve is actually a paired structure. So you have two of them, like two thumbs and two kidneys. You have one on each side. It starts at the level of about the level of your ears in your brain and travels down your neck, across your chest and abdomen. Along the way, it's the longest of what's called a cranial nerve, nerves originating from your brainstem that go into your body. And it's the longest of those 12 pairs. But along the way, the vagus nerve is like an information superhighway. It's like a transatlantic cable connecting your body to your brain and your brain to your body. So I already said, you said vagus nerve. I already said you have two. And now I'll clarify that a little bit more. On each side of your neck, where the vagus nerve is traveling, inside of it, you have about 100,000 individual nerves. So you really have 200,000 vagus nerves. And what it's doing is carrying the information about the function of all your organs that you never think about all day long, back and forth between your body and your brain. This information is the basis of reflex circuits. Reflexes, like when the doctor taps your knee and your knee pops up and you said, "Who did that?" It's reflexes that are operating to control how your organs are working. And essentially, the information your vagus nerve is carrying is fundamental to keeping you healthy. So that's why it's so important. And there are now billions of web impressions and social media postings on this. There's a lot of interest in the vagus nerve and its relationship to health.
Of the 200,000, let's call them informational processing units, how many of these, of the 200,000, have been mapped so that we could say, number 132,336 does this? Is it 5% has been mapped? Is it 95% has been mapped? Where are we in that process?
When you go to level of fiber specific mapping, it's zero.
Wow.
Yeah. So my colleague, I'm sitting today at my lab at the Feinstein Institute, and my colleague upstairs, his laboratory, Stavros Zanos, is actually leading a consortium, a major NIH-funded consortium of several centers, and they're producing the first detailed fiber-specific maps of the human vagus nerve. They harvest vagus nerves from cadavers, and they slice them 5 microns at a time, and then stain each slice with various dye stains, like ancient pathologists and anatomists used to do. But they're also applying technology like single cell RNA sequencing and very sophisticated protein mapping using antibody stains. And then they're reassembling this and building computer models, almost like a CAT scan, three-dimensional CAT scan of the human vagus nerve, following where all the individual fibers go, starting from the level of about the neck down to all the organs, the liver, the pancreas, the intestines. So yeah, we're building those maps now with all the interest in the vagus nerve and all the quote unquote vagus nerve experts out there talking about do this, that, or the other thing. The first question you ask, and the answer is zero. Much of what's being talked about today is actually pointing to anatomical maps that go back 50 or 100 or more years.
So if we compare that zero to, let's say, our topographical understanding of the actual brain, that number is obviously greater than zero. So what is it, why is it that so much attention has been spent on, trying to understand at least, I mean, not every single neuron and every single synapse, but we do have an idea that, if there's a stroke here, you lose your ability to for language. So there is somewhat of some good mapping. Why has there been so little progress with that particular nerve?
It's a really good question. I don't have a great answer for you on that. As a general rule, there's a tremendous interest in mapping the vagus nerve now. I told you the story of what Stavros is doing upstairs for human vagus nerves. In animal experiments, in basic neuroscience, basic neuroimmunology laboratories, there's a tremendous interest in applying very sophisticated molecular and genetic techniques to draw detailed maps of the vagus nerve in mice, for instance. So there's a lab at Harvard in Boston led by a colleague and friend named Steve Lieberless. And Steve's lab has done some absolutely brilliant work doing fiber-specific mapping in mouse vagus nerves. This is really surprising results. So let me just give you another, for instance.
Sure.
Mice vagus nerves are obviously much smaller. Mice are smaller than humans. And say there's 5,000 fibers in a mouse vagus nerve. Steve and his students and his postdocs have mapped the fibers that control breathing, and it's like 100 or 120 fibers. Imagine that. And you would have thought something as important as breathing being controlled by the vagus nerve, it would be a much bigger number of fibers. In our own work, collaborating with other labs as well, we estimate that the fibers that in the vagus nerve that turn off inflammation, which is where our main interest has been, we estimate that in humans it's less than 1,000 fibers. It may be as few as a few hundred fibers. So if it's a few hundred fibers controlling inflammation and you have 200,000 fibers, the complexity of making these maps is really amazing. But we have the tools now in animals, in laboratory animals, laboratory experiments. We have the tools to go fiber by fiber by fiber to build the maps. And someday, when we are able to apply similar kind of tools to humans, we'll have all the answers to this. But yeah, no, there's a huge opportunity for research there.
So does the fact that now you've got an explosion of computational ability in, computational modeling and, computational biology, is that going to, expand the ability of researchers such as yourself to be able to quickly map this? Because in a sense, maybe, so I'm going to answer the question that I originally asked you. Maybe you couldn't have mapped it, and the reason why it was at zero is because you were computationally limited. You weren't able to do the types of things that now you're talking about where they're slicing and so on. Could it be as simple as that in terms of once we get the supercomputers going, the quantum computing going, we might be able to crack the whole mystery?
I think that computing is part of the equation, and yes, as we embrace this explosion in AI and in the explosion in the efficiency and the capacity of computing, yes, things will go faster. But biology is complicated, and there's things that computers can't do without experimental data and input. And there you get advances, you get staggering advances when the technology advances. And so I'll tell you something that we're really excited about now in neuroscience and in neuroimmunology. It's a technology called trapping, and what you can do now, and this brings together this whole line of questioning about maps, because when the kind of maps you and I are talking about, it's not just a picture of the neurons. It also is a description of what their role is, what they're doing, and how they work. And that you can't predict that from an AI program. You have to measure it. You have to try the experiment. The way we do that now is with a really cool technology I said called trapping. So imagine through genetic engineering of a mouse, you can rig the neurons in its brain so that when those neurons are activated by a specific task or a specific memory or a specific event, they turn themselves red. It's almost like a self-tattooing neuron. Now we've been doing this, and this has started. Actually, the first use of this in immunology, neuroimmunology, was by Ashia Rolls in Israel, and her brilliant paper in Cell a few years ago. And what we can do is we can produce inflammation in a mouse through a chemical trick or by studying mice that have conditions like colitis or arthritis. And you can say, what are the neurons in the brain that disease, that condition is activating? And you can go back and identify those neurons. You can wait 2 weeks. You can let the colitis go away or let the inflammation that we caused in the mouse, let it go away. And now you can selectively reactivate those brain neurons without trying to produce any inflammation in the mouse or doing any chemical tricks. And the activity of those brain neurons will cause the colitis to reappear, or the arthritis to reappear, or the other inflammation that those neurons are associated with. That means having the memory in your brain of the inflammatory state produces the inflammatory state in your body.
Wow.
That's the right answer. Wow. So now we can say, well, where are those signals traveling from the brain to the body and back? Some of them are in the vagus nerve, and we can draw maps of those fibers from the neurons in the brain to the fibers in the vagus nerve to the location in the intestine or wherever else we're studying inflammation. But that's what we're able to do now. You can't, a computer model, even a very sophisticated AI model, can't conjure that up. It has to start with the observations from these kind of modern technologies.
Only because we're on the theme of computers, I'll ask one question about AI and then we'll go back to how you chose that particular interest in studying that particular, system. Uh, do you foresee ever a day where there is no need for Dr. Tracy performing the surgeries because the robots will be so uh, their dexterity will be so. I mean, I saw recently on, I think it was an Instagram reel where these robots were peeling like some unbelievably small minutia that you could have never imagined that they would have that level of dexterity. Is this something that is way in the future science fiction, or are many people in medical fields, whether it be in neurosurgery or certainly like in radiology, for example, where you have the pattern recognition that the AI can come up with that oftentimes beats the ability of the human? How does AI challenge or contribute or help neurosurgery?
In the way that you just described, I think you're going to see, who was it? Ernest Hemingway said, change happens slowly and then all at once, something like that. I think that we're living through now the change happening slowly. And there's a good reasons for change happening slowly in medicine. Even in your own personal case, you don't want your own doctor chasing every shiny new object every 5 minutes, right? You want careful, conservative thinking to be the first do no harm to guide the early adopters and the early adopters and the early decision makers. That's all fine. Well, in that scenario, change is already happening, right? As you said, in the medical fields that are highly image oriented. You mentioned radiology. There's also dermatology and pathology. Even now, AI guided and computer assisted, if not computer, I'm not going to say independent, but computer deterministic evaluation of colonoscopies, right? There are products now out on the market where the camera is feeding all the information straight into a computer that's reading every single image and picking up things, polyps and potential tumors or other problems that the doctor may or may not have picked up. That means we're one step away from colonoscopies being done by swallowing the camera. Why do you need the doctor to hold the tube if the images are all being read after the fact by a computer? So these things are happening as we speak. I mean, if you even in psychiatry, right, where you have this goes back decades, where psychiatrists have been scanning web searches, search engines, to pick up diagnosis of early depression, anxiety, or even schizophrenia from kids as they do their Google searches, and a certain combination of words are being studied as possibly being warning signs that this person should be helped, should seek help. These things are all happening and have already happened in some cases. So when you look at the power of robot assisted surgery today, whether it's for endoscopic surgery with GI surgery or urology procedures in other gynecological procedures or neurosurgery, as you said, I think absolutely robots are going to be more and more capable of doing more and more of the surgical intervention with less and less of the human intervention.
Yeah, I'm just brainstorming here. So I'm thinking back of some of the research that I had studied when I was a doctoral student, where if you show people that the likelihood of you being accepted into a program, if you use an actuarial model, just a mathematical model, actually results in better outcomes than if you use a human decision maker. Because the human decision maker, maybe their blood sugar is low because they're hungry and now they're pissed off. So the exact same file that I might have said, yes, okay, get him into Princeton. Now I say, screw this guy, he's not going to get into Princeton. So even when you tell people, Kevin, that it would be in their best interest to use an actuarial model, they don't feel comfortable in giving their future away to a cold mathematical model. Might it also be the case that even if we ran studies showing that the likelihood of a neurosurgical robot of making an error is lesser than a human one, do you think that it would be the case that people would have reticence? I want a real human being working on my brain, not some cold algorithm. Does that seem reasonable for me to expect that they would have that bias?
I'm not a psychologist. I'm not an expert in this space, but I will tell you first. I saw a statistic recently, and like I said, I don't know if it's true, but it was from a reputable journalistic source that a significant percentage of job applications to major corporations today are already being screened by AI. So in one way, you can say there's already been an abdication to that model, the actuarial model. And I think the same thing happens in colleges, where a large number of the college applications are already being screened by AI. And as far as what people will prefer for when they seek their health care, I mean, there's the old neurosurgery joke, right? If you ask a neurosurgeon who the three best neurosurgeons in the world are to solve that patient's particular problem, they have a very difficult time thinking of the names of the other two. So it's complicated. I think medicine is not. I think as doctors, and I no longer treat patients. I'm not practicing now. I retired from my clinical practice. I run my research lab now full time. But when you think about what we're going through, and maybe this is an important punctuation point on this whole conversation, AI is here. AI is not going away. AI is going to be more and more involved in all aspects of our lives. That's and it will replace the way we do some things. Our obligation now as healthcare leaders and providers is to make sure that we insert the humanity, the humanness, the human touch into healthcare, because AI can't do that. And it needs to be sort of constantly reiterated, discussed, and reminded that patients with the highest trust in their physicians or in their healthcare providers have better outcomes. This has been studied and proved 10 ways to Sunday. If you have those patients with the highest confidence, the most belief in their caregivers have better outcomes. There's something about the human touch and the interaction of compassion and caring, especially when, frankly, medicine runs out of options. You still have that compassion and caring that we cannot lose sight of. It has to remain on the critical path of what we do in all of medicine and surgery.
Beautiful. I'll come back to your book and one particular term, which I'm sure you'd be happy to talk about, bioelectronic medicine. So let's table that for a second. But since we're talking about neurosurgery, do you mind if I ask why you decided to leave your clinical practice? Because one of the questions I was gonna ask you is that you wear many hats. Which one do you prefer and why? And has that preference shifted across your career? And it would seem to me that maybe now perhaps you're more excited about your research than you are about the clinical. So walk us through all those decisions. And again, I ask these questions first because I'm interested in people that I talk to, but as a psychologist who studied psychology of decision making, these types of decisions always fascinate me.
Well, I mean, it's a long story, but to tell it in brief, my mother died of a brain tumor when I was 5, and it came as a very sudden surprise to all of us. My father, her father was a professor of pediatrics at Yale in New Haven, Connecticut. Came as a surprise to him. My infant baby sister and my younger brother, all of us were obviously devastated by this. And so all my life, I've been very sensitized to what is neurosurgery and what is the impact it can have. By the time I was a teenager, I had really decided I wanted to be a scientist. All my life, I knew pretty much as long as I can remember, I wanted to have a laboratory, I wanted to invent things, and I wanted to understand how to invent things that could lead to cures. I just thought it was such a fascinating path. And so I was on that path as a chemistry major in college at Boston College, and then making a career decision of getting a PhD in chemistry, where I could then go learn to make pharmaceutical drugs, or getting an MD and learning how the diseases actually worked. And that's the path I chose, obviously. And then in medical school, you have to pick surgical versus non-surgical specialties. The decision to become a neurosurgeon, it's certainly an interesting story now, looking back, but I didn't become a neurosurgeon because my mother died of a brain tumor when I was 5. I became a neurosurgeon because when I finished my training in the early 1990s, so as a fully trained neurosurgeon, the neurosurgery departments had a lot of resources. And this was a time when the departments, whether it was neurosurgery or medicine or general surgery, the departments with the most resources had the biggest opportunities to support research laboratories. And so I could combine a career doing neurosurgery 1 day a week and then running a big laboratory for the other 6 days a week, which is what we all did. We worked in the clinic a day a week, and then we became obsessed with our laboratory projects. So I always had a career that combined these interests of doing research to discover ways of trying to help people and understanding how diseases worked. And in neurosurgery, I wouldn't trade a minute of it away. I loved learning how to do neurosurgery. I loved interacting with the patients. I loved doing neurosurgery, but I wouldn't trade away a minute of the years I spent in the laboratory working with brilliant graduate students and brilliant postdocs, trying to unravel how the universe is assembled. Take it apart piece by piece, and then build it back together again, so that you can invent new therapies. And we've been fortunate because we've had a couple of wins in those stories, and it wouldn't have happened, I think, if I wasn't acutely aware from my training of how disease affects people, and how the importance of the brain and the nervous system in those connections and those responses. But it also wouldn't have happened if I hadn't taken the time to spend years in the laboratory and learn the basic science principles of how do you do an experiment to take apart a complex molecular interaction and break it down to the simplest assemblage, and then reconfigure it in a way so what's broken is now fixed.
Beautiful. When I was deciding after my undergrad what to go into, one of the things that I thought of doing was to do an MD PhD. I was very much interested in potentially psychiatry, just because I was interested in behavioral sciences and so on. And the reason why I would have been interested in doing an MD PhD is exactly what you intimated, which is I would have liked to once in a while, be doing the helping others, but I was at heart, I was somebody who wanted to solve puzzles. And so I thought that the MD PhD would work out. Later, I ended up not pursuing that goal because I was quite disheartened, and you'll tell me if I'm right or wrong, by the amount of what seemed to be quackery in the mental health professions in general, right? So it went from all the Freudian stuff where it was all environmental, mommy didn't hug you enough, or maybe she hugged you too much, that's why you're schizophrenic, to completely the opposite, where everything became pharmacological. And like most things in life, the sweet spot is somewhere in the middle, a bit of listening to the patient and maybe being empathetic, and when need be, giving that pill is probably the right. So I could have followed you in that MD PhD. I know you didn't pursue a PhD, right? You got your right. All right. Let's go back to the book, and let me mention it again. I don't have the physical copy yet. I think your assistant sent it to me to my university address here, where I'm on leave from my university. But let me read it. The Great Nerve: The New Science of the Vagus Nerve and How to Harness Its Healing Reflexes. Tell us all about bioelectronic medicine.
The book tells the story of something I mentioned briefly earlier, which is that signals in the vagus nerve can turn off inflammation. And we made this discovery quite by accident. You asked about the origin story in my own career case. The origin story of this accident is that we were studying animals that had a stroke, cerebral infarction. And the idea was the stroke causes inflammation in the brain, which it does do. And we put a molecule into the brains of these animals to turn off the inflammation, which it did do. And we were very happy with that. And that was what we expected to see. What we didn't expect to see was when we put these molecules in the brains of these mice, this is back in the 1990s, that the inflammation in the body of the animals was also turned off. So this was a real head scratcher. This is a real WTF moment, because there was no way to understand how a molecule in the brain of a mouse would turn off inflammation in the body of the mouse. And the key experiment came when we cut the vagus nerves that were carrying the signal from the brain to the immune system in the body. And that was a real sort of, as I said in the book, we don't say eureka in the lab anymore. We say, holy shit. So, because once we realized there were signals in the vagus nerve that were acting like the brakes on your car to stop inflammation, then we realized we should be able to make a nerve stimulating device, a small battery powered electrode, and implant it in the vagus nerve of humans, because we already knew that could be safely done. As a neurosurgeon, it was being done to treat epilepsy patients back in the 1990s, so it's safe. And if we could do in humans what we were doing in the mice, then we should be able to treat conditions like rheumatoid arthritis and inflammatory bowel disease. So back in 2007, I started a company called SetPoint Medical with a colleague from Harvard named Shaw Warren. And now, 18 years later, literally just a couple of weeks ago, here at my center, we implanted 2 patients because the FDA approved this idea as a therapy for rheumatoid arthritis around the first of August. That whole story made the front page of the New York Times about 3 weeks ago.
Wow.
And and the reason is that this now is a therapy that'll be available to people with a very serious condition, rheumatoid arthritis, that's currently treated with very dangerous, expensive drugs called biologics, things with names like anti-TNF and anti-IL-1. And these drugs, right now, we're trading off the treatment of inflammation with these drugs with the side effects of immunosuppression. And with the side effects of potentially going bankrupt. Some people have to spend $50,000 to $100,000 a year on these drugs in the United States, and they only work half the time. So now the question is, will some of these patients who are not gaining benefit from these expensive, dangerous drugs, will some of them have a immunoregulator, it's called, implanted in their neck as their primary therapy for rheumatoid arthritis? And the early data are very, very promising. That's what's happening as we speak.
So, but what, so how big is that device?
It's about the size of a multivitamin. It's less than an inch big. I
And,
mean, you could
and
swallow it.
what's the energy? I mean, do you have to change the battery? How does that, is it like a pacemaker?
It is a it's a fully self-contained device. It has a battery which is fully rechargeable, so it's implanted once for at least 10 years, maybe for life. You recharge it by putting a collar around your neck, and then charges right through the skin once a week. The there's a motherboard that controls the electrodes. There's an antenna that communicates to the doctor's tablet or iPad, and the electrode sits right on the vagus nerve, and the little device about the size of a multivitamin is wrapped in a, looks like a pea pod, a silastic pea pod, and the neurosurgeon puts one stitch through the top of this pea pod that closes over the device and holds it in place on the vagus nerve at about the level of your Adam's apple through an incision that's an inch or an inch and a half long. Once the incision heals, well, with your beard, no one would ever see it on you anyways. But even if you don't have a beard, the incision, it travels in the skin creases, and you won't notice it. You won't know anything's there.
Wow. So in the ecosystem of bioelectronic medicine, so I mentioned, I guess pacemakers would have been an early manifestation of that, the stuff that you're doing. And to link it back to, we were mentioning briefly earlier, psychiatry. So I'm thinking, let's say about transcranial magnetic stimulation. Are all of these things that I just mentioned under the general rubric of bioelectronic medicine?
Yes and no. I would say that let's do pacemakers, cardiac pacemakers first, because they're historically they go back to the 1950s or so, and that they're not really medicine, right? They're really a structural thing that or an artificial hip, for instance. It's very structural. And in the case of a pacemaker, you've got electric sparks, electric pulses that activate nerves that activate the heart to beat, right? So that's not very drug-like. It's very mechanical. What bioelectronic medicine captures in its definition and what it delivers in its promise is the idea of using devices to target nerves as drugs. So in the case of rheumatoid arthritis and the immunoregulator stimulating the vagus nerve that we just talked about, what you have is actually a drug target. So let's pick a cytokine. Cytokines are inflammatory molecules. They were much talked about during COVID. They have names. They're proteins. They're made by white blood cells, and they have names like TNF and IL-1 and IL-6. So right now, if you're a drug company, you might pick TNF as your drug target. And you say, I want to make molecules that suppress TNF or neutralize it. You make your molecules, you screen them, and then you prove they're safe and effective, and then you sell them, and the patients inject them. Bioelectronic medicine is different. Bioelectronic medicine says, we're going to start with our same drug target, TNF, but we're not going to make drugs against TNF. We're going to identify nerves that produce molecules, neurotransmitters, that turn down TNF in situ, in place. Then we're going to say those nerves can turn off TNF. Now I can make a device to control the nerve to turn off the TNF, and the device becomes the therapy. And that's what bioelectronic medicine is. So we've done this now to treat inflammation, as I said, in rheumatoid arthritis. It also seems to work in inflammatory bowel disease. In animal experiments, it works in multiple sclerosis. There's evidence from diabetes. There's evidence from other inflammatory conditions. So we understand the basic principle for stimulating the vagus nerve circuits that regulate inflammation. And there's a lot of work going on in laboratories around the world replicating all this, as well as in replicating and new clinical trials. But that's the tip of the iceberg, because there's so many other nerves in your body that are controlling the activity of other immune responses in other tissues and in other organs. It should be possible to work our way through other diseases and conditions and target other nerves with other devices. So that's the field we call bioelectronic medicine.
Okay, is it, and forgive me if this is a dumb question. It, in much of the responses you give, the I word always comes up, inflammation. Should one presume then that the bioelectronic approach that is replacing, in this case, the pharmacological approach is one that is largely working with the cluster of inflammation diseases, or it could be pancreatic cancer or whatever, something that doesn't necessarily involve, an inflammatory response. Oh, but bioelectronics can also go down that pathway.
So you know what I'm going to say, right? I'm a scientist, and I don't like to predict the future. So we try not to presume anything. We try to form hypotheses, do experiments, and look at the data. Now, the data for today are in inflammation, and many clinical trials have now been done. And as I said, rheumatoid arthritis has received FDA approval as an indication. But the laboratory data for many other inflammatory conditions is very promising. And when you approach the problem of inflammation in a reductionist way, you go down the funnel to look at the simplest first principle mechanisms. We know a lot about the first principle mechanisms of what causes inflammation and what drives it. And that gives us the opportunity to connect those back to nerves that we can then connect to devices. So that's a huge research opportunity. But about two more important points. The, when you look at the conditions that kill 2/3 of the people on the planet Earth every year, so every year 60 million people die, according to the WHO. 40 million of those people die of conditions which are related to inflammation, which is, you said, sort of the big I. That is inflammation a unifying theme? It is right now, because we can do the reductionist work, we can do the clinical trials, and we can ask the important questions that affect 2/3 of the deaths on the planet Earth. But maybe the most important answer is about the future is that I don't have a crystal ball, and I'm a scientist, and I don't like to make wild guesses. But if you know the size, the area of a pond, and you know what percentage of the pond is covered in pond lilies, and you know the doubling time of the lily pads appearing on the pond, you can make an accurate prediction about when the pond will be covered in pond lilies. That's not really predicting the future. That's dealing with today and knowing what the reality of the facts of the matter are. So in that light, I'm actually quite confident that millions of people with conditions related to inflammation are going to be treated with an implant, a small device the size of a multivitamin to stimulate their vagus nerve or some other nerve in the coming years. I think this is going to be a new way of thinking about how to treat inflammation. I think that process has started, and I don't think it's going to stop. I think it's going to accelerate.
Nice. I saw you before we did our start our conversation. I tried to this morning listen to a chat you held, I think with a fellow neurosurgeon. I can't remember his name, a gentleman from University of Miami, and he asked you a question which I'm going to ask again, maybe hoping for a different answer. He had asked you, have you faced a lot of resistance? That actually, I perked up when I heard that because. Uh, in my current book, so I'm writing a book right now called Suicidal Empathy. What happens when you have a noble virtue like empathy that becomes dysregulated? You end up with all sorts of, foreign policy and domestic policy problems due to suicidal empathy. So I have a chapter where I talk about things like what settled science, right, as a form of epistemological empathy, right? It's settled, shut up. And so therefore, the orthodoxy says it's this, and then if you're a heretic, then we're going to ostracize you. And I give a whole bunch of examples, many of which are from medicine. One that of course you're undoubtedly familiar with, Semmelweis, right, with the hand washing, probably saved more people than most other working physicians in recorded memory. And yet, of course, it didn't turn out well for him in terms of his lifetime. Now, the reason why I said, because when that gentleman asked you, you said, "Oh, I haven't really faced any blowback." Do you still hang on to that? And if so, isn't that surprising? Isn't it the case that whenever you have someone that's doing something that is non-orthodox, you should be expecting blowback?
So I don't remember exactly the answer I gave before, and I'll try to give a different answer this time, or a similar one, but different. I think when I referred to not a lot of blowback, I think that really was in the context of from the side of immunology.
Okay.
So a lot of the work that I did with my colleagues here at the Feinstein Institute, and before that at Rockefeller University in New York City, we were interested in unraveling the basic building blocks of inflammation at the level of individual molecules. And I spent years identifying the activity of a molecule that I said before is called TNF, and how if you block TNF with monoclonal antibodies, you can use these as drugs to treat inflammation. And so when I migrated with my colleagues into studying TNF as the target of a monoclonal antibody to controlling TNF using electrical signals in the vagus nerve, the immunologists were very surprised because the nervous system and the immune system were viewed as sort of separate entities. They were firewalled from each other. But they didn't have any reason to not believe me because of the background I came out of from studying TNF for many, many years. And I was a neurosurgeon. What was interesting was, I would say, those that resisted this idea, and there were many, they didn't come after attacking me. They just didn't talk about it. If you one way to well, if your child is acting out, not that any of my children ever acted out, but one way to, obviously, to get back at someone who's acting out, doesn't have to be a child, can be an adult at a cocktail party, is to just ignore them.
Right.
And so there was a lot of people that did that. And frankly, most of them were in neuroscience. The immunologists in their own way, they thought, wow. I think the immunologists thought, wow, it's interesting, it's kind of cool. Have no idea if it's going to work, and maybe it'll work, and we'll hear about it someday. Well, that took 18 years or 20 years to prove to everybody that it could work. On the neuroscience side, they didn't. I would say they didn't really embrace this until the last five years or so. But now, this space called neuroimmunology, these relationships between the brain, the nervous system, and the immune system, it's one of the hottest fields in all of science. I participated in a meeting just a couple of weeks ago here in New York City, hosted chaired by Brian Kim and David Artis, two of my colleagues across town here in New York. And that meeting was attended by like 300 people in person and hundreds more online. And that's a big scientific meeting for a new field. So neuroimmunology is now exploding, and there's very little resistance to the idea that we're going to be making lots of new therapies that are going to help lots of patients. The obstacle now is the classic barriers to adoption. You've got the early adopters, you've got the middle 2/3, and you've got the late adopters, or the laggards. And the reason I wrote the book The Great Nerve, was to tell these kinds of stories, because at the end of the day, with all due respect, doctors don't drive big changes. Patients,
Right.
and patient demand and patient activists. That's what really drives change in medicine. And so I wrote The Great Nerve as a way to be a resource for people who wanted to know, what is the science of this great nerve? What is the medical and therapeutic implications of this science? And where are we now with the FDA approval for rheumatoid arthritis? And then the third part of the book, what can we do about this at home? What about all the billions of web impressions that say, do this, that, or the other thing for your vagus nerve? What's true, what's false, and what needs more research?
Yeah, I mean, earlier when you mentioned, I can't remember in what context you said, oh, there are all sorts of experts. And I think you might have even used air quotes. I take that to mean that so there's kind of a bro science where everybody is not a neurosurgeon, and with your scientific imprimatur that offers all sorts of advice. Is that what's happening in this particular ecosystem?
Right. Yes, that is what's happening. So there's reason why people point to the vagus nerve as a way of, of, of maximizing and optimizing good health. And people will come up to me after one of my lectures or write me an email and say, I want to stimulate my vagus nerve because that'll make me happier, or it'll make my heart healthier, or stop my inflammation. And I say, that's great. You have 200,000 vagus nerves. Which one do you want to stimulate, and how are you going to do that? Because that's where it breaks down. So one thing that's talked about is very, very popular is humming or chanting. Okay, fine. There's a vagus nerve goes through your neck, sends off a few hundred fibers to your voice box, your Adam's apple, your larynx. And when I'm talking to you right now, I'm exercising my vagus nerve. Does that mean I'm turning off the inflammation in my immune system? Well, I don't know. Those are separate fibers. Does that mean I'm regulating the glucose in my liver? Well, I don't know. Those are separate fibers in the vagus nerve. I can walk and chew gum at the same time, and presumably you can too. And that's because some fibers have some jobs and other fibers have other jobs. So at the end of the day, when you chant, are you exercising your vagus nerve? Technically, you're exercising the fibers in your vagus nerve that go to your larynx. As I said, say it's 500 fibers. What are the other 199,500 fibers doing? All the same thing? I don't think so. And that's the opportunity we have now. Back to the analogy of how many fibers you need if you're a mouse to control your lungs, 112, 120. It's a very complicated system. And the first thing we talked about in this podcast was, can we identify each and every fiber and what its function is and what its path is? And today in humans we cannot, but someday we will be able to. At which point, when we know all the maps and all the functions and all the origins and insertions of all the individual fibers, we'll be able to, I think, do some very powerful things on the side of therapy.
Okay, one more question because I want to be mindful of your time. We're coming up to the 1 hour mark. One question that might be a bit out of your wheelhouse, but I hope you'll indulge me. I'm going to try to tie in some of my scientific interests and see if it could connect with some of yours. And the reason I asked the question about the resistance, from the orthodoxy and so on, is because so I apply, Kevin, evolutionary biology principles and evolutionary psychology to study human behavior. The idea being that you can't simply assume that human beings are cultural animals. Our biology does matter. Now, to you, someone steeped in biology, it might seem like, well, no kidding. No, no, who doesn't think that? Well, if you're called a social scientist, you actually think that that's the most heretical thing that anybody could ever say. Because for most social scientists, what makes us human is that we transcend our biology. We are cultural animals. And so I spent my whole career fighting against social scientists because I want to talk about evolutionary biology and how it helps us shape our behavior. Okay, so having set that up, there is a field called evolutionary medicine that seeks to incorporate evolutionary principles in the practice of medicine. Now, it may or may not surprise you, Kevin, that most physicians, including, I suspect, neurosurgeons, are not trained in evolutionary theory because they operate at the proximate level. Pretty much every single word you said when you're offering some scientific explanation today operated at the proximate. The proximate means the how and the what of a mechanism, how this works, which is perfectly fine. 99.9% of science operates at the proximate. The ultimate explanation, though, is the one that answers the Darwinian why, which is why would it have evolved to be of this form? So, having given you sort of this background, as a neurosurgeon, has there ever been an infusion of ultimate level thinking, whether it be when you're practicing as a neurosurgeon or when you're tackling your research?
I think tackling the research, this has happened many times. This perspective has happened many times. Well, look, Plato said it, right? Heal the soul, heal the body. Sick, the soul is sick, the body is sick. I think what I've come to appreciate is you can have it both ways, if you will. If you view the organized responding organisms as having sort of three components, you have the reflexive components in the body that are reacting to changes in the environment. You have the emotional component in the brain uh, responding to those body changes, as well as responding to the thoughts from the thinking part of the brain that can be generated. And it's a funny thing, but I tend to build an operating model around the separation and integration of those three components: the reflexive components, the emotional components, and the thinking planning component. But here's the key. And Charles Sherrington, one of the two fathers of neuroscience, said it best back in the 19 teens in his classic book, The Integrative Action of the Nervous System. He said the following. He said, you have to understand a simple reflex circuit. Reflexes all begin with a change in the environment, with a sensory input. Second, the reflex sends the input signal activates an output signal. It tends to converge back to the place of the input signal. Third, he said, you can assemble reflexes together and build a complex nervous system. Which means at the end of the day, there's no such thing as a simple reflex because all the nerves in the nervous system are connected, ultimately. Now, in the context of this model, this behavioral model or this reflex model, the part that's overlooked most frequently, I think, by everybody, not either extreme in your audiences, is that everything starts with a change in input. So you've seen that, you probably know this work better than me, but you put the professional baseball player in a simulator and you throw the fastball at him and the muscles swing before he decides to swing the bat. So in other words, consciousness, the conscious explanation of what's happening in the body and probably in emotions too, to some degree, is 400 milliseconds late to the party. So once you understand that, it changes everything about how you approach behavior, even complex behavior. The inputs in the body can influence your emotional state in a way in which you are not conscious of. Right. That's called interoception. And this is one of the hottest areas of science. It's part of neuroimmunology because right now you could be sitting there. You and I just met today. You seem like a very happy, optimistic guy. I'm a happy, optimistic guy. But if we had a little inflammation simmering away in our liver, even if it didn't hurt, even if it didn't have a conscious symptom, might that inflammation make you depressed or me depressed? Well, the experimental evidence is absolutely yes.
Wow.
The presence of inflammation in the body of an animal or a human can by sending inflammatory signals into the system, into the vagus nerve and other nerves, produces a state which is indistinguishable from depression and sickness behavior. So is it fair then to say depression has to be treated in the brain with serotonin, SSRIs, or with talk therapy or whatever? Maybe in some patients it's a top-down problem. But the evidence is clear that in other patients it can be a bottoms-up problem. And I don't think some of the models that we use today accommodate that in a cohesive way, like I'm answering.
Very nice. Last question, and then we'll say goodbye offline. You've written this book, The Great Nerve. Could we ever hope to expect like Henry March, which, by the way, I recently read his book. I don't know if you know. Do you know what that is? Yes?
Yes, I do.
Yeah.
Yes, a great writer and a neurosurgeon.
Exactly. And so I just read his book, maybe in honor of my son who was interested in neurosurgery as a 13-year-old. But, in his case, he's talking about his clinical tales, right? Oliver Sacks, who was a neurologist, not a neurosurgeon, also became very famous as an author, just talking about all these unbelievable cases that he'd face in his rounds. Can we ever expect Dr. Tracey to come up with a book where he blows us away with some of his clinical tales, or are we going to stick to the hardcore science?
So the Great Nerve has clinical tales, and I tell this I tell the story of patients that I've had the good fortune of meeting. For instance, Kelly Owens, who famously monitored and posted her whole life story in blog posts and in her own writing online and in private. Her story of facing the challenge of inflammation from inflammatory bowel disease, Crohn's disease, that was complicated by serious inflammation in her joints, which looked like rheumatoid arthritis. To make a long story short, Kelly was one of the first patients treated in a clinical trial for vagus nerve stimulation by the company I started, SetPoint Medical, and she's in complete remission. And
Wow.
so, despite having spent more than $1 million on various drugs that failed to help her, despite having spent years in and out of hospitals from New Jersey to New York to Minnesota to Hawaii and back, what helped her was a vagus nerve stimulator. And so her story, I wrote it and it still makes me cry when I reread it. It's a happy ending. What we hope from these stories is that the word gets out so that we can shorten the adoption barriers, number one, and number two, so that people have access to calls to action and messages of hope, and number three, and perhaps very importantly, that we can take all this in light of what we know today and what we still have more work to do. Look, Kelly's story is a dramatic. I've met many patients with dramatic outcomes. It doesn't mean these ideas or these therapies are going to help everybody. They won't. We know from all therapies in medicine, some people have great responses, some people have no responses to the therapy, and some people have okay responses. But we're early days. I'm very, very excited. And yeah, at the end of the day, like you, the reason we all get to do what we do is not just for the science or just for the medicine. It's all about the patients, and you meet a couple patients along the way who feel better, and it's all about them.
Well, you're a hero. Thank you for all of your great work. Pleasure meeting you. Stay on the line so we could say goodbye. People, get out there and buy The Great Nerve. I'll be sure to read it. I haven't read it. I only peruse quickly through it, but I'll check it out. Thank you so much for coming on, Kevin, and come back anytime. Cheers.